Hello everyone, I am Abdul Aleem Seeni Mohamed and I would like to present about Peng-Robinson equation of state based on key group contribution and calculation of nitrogen gas solubility in methyl methacrylate dimer. Polymers commonly can be found and used in our daily life. For instance, polystyrene, polymethacrylate, and polyvinyl chloride. These polymers commonly synthesize via free radical polymerization, which involve initiation, propagation, and termination step. During polymerization process, free radicals are formed from molecules in initiation. Afterward, those free radicals will bond together to form monomers in propagation. Then the polymerization will stop in termination when the long chain of polymer is formed. However, free radical polymerization is conducted in presence of air, not under vacuum condition. Due to oxygen in monomer, it will increase the induction period and affect the quality of polymer. Hence, it is very important to remove oxygen from monomer. There are several methods to remove oxygen, which are freezing and evacuation, vacuum distillation, and bubbling techniques. Therefore, the bubbling technique is more commonly applied in industries, but this procedure is just depends on empirical. However, there is limited solubility data of gases in monomer available for redesign the polymerization process. In previous work, benzene, styrene, and divinyl benzene was investigated for nitrogen and oxygen solubility. These three compounds was having the same CH group, so we decided that it was the key group. The solubility of nitrogen in benzene, styrene, and divinyl benzene at 313 Kelvin are shown in the figure. From the figure, x-axis is a mole fraction of nitrogen or oxygen and the y-axis is a pressure. For nitrogen solubility, open square indicate benzene, closed circle indicates styrene, and the open triangle indicate divinyl benzene. These three compound solubility are aligned on a straight line, as well as for oxygen solubility in this compound also showing the same trend as nitrogen. From the solubility data, we deduce that the CH group is not the key group. So we expect the solubility would depend on the number of aromatic ring in the compound. As we can see in the figure, these three compound has the aromatic ring. So the aromatic ring could be the key group. Moreover, styrene is one of the most popular monomer and is very similar to MMA. Hence, we would like to investigate the existence of key group in MMA and its derivative. The solubility data of nitrogen in MMA was collected from our previous work. Meanwhile, a hypothetical gas solubility data of ethylene glycol dimethacrylate (EGDMA) was made by modified Peng-Robinson equation of state with group contribution model. The reason EGDMA was selected is the molecular structure of EGDMA is the mirror image of MMA. In other words, we call it as a dimer of MMA. As we can see in the figure, molecular structure of EGDMA is 2 times of MMA. If the key group exists in MMA, the solubility in EGDMA is expected to be twice of MMA. The figure 2 shows solubility of nitrogen in styrene, MMA, and EGDMA at 313 Kelvin. Those closed rectangles indicate the nitrogen solubility in styrene, and the open circle indicate the nitrogen solubility in MMA. Both data are obtained from literature, while the closed circle indicate the nitrogen solubility in EGDMA, which is hypothetical value. The EGDMA is require half the pressure of MMA to have same nitrogen solubility as MMA. As I mentioned earlier, the EGDMA is 2 times the solubility of MMA. Normally, the solubility obeys Henry's law up to atmospheric pressure, which is around 0.1 MPa. But for the styrene and MMA, obey more than that, which is up to 4 MPa. This condition indicates the existence of key group. Since the EGDMA is derivative of MMA, we expected the key group might exist in the EGDMA as well. This one is collection of experimental data. Next, I would like to explain the theoretical background and modeling. In this research, we employ prediction method by using equation of state. The data from this work is correlated with Peng-Robinson equation of state 1976 and mixing rule. The parameter required for Peng-Robinson equation of state are critical pressure, critical temperature, and eccentric factor. By applying the critical parameters and eccentric factor into equation 2, 3, and 4, we can utilize Peng-Robinson equation of state. The mixing rule is necessary because solubility is linearly dependent on pressure. So in this study, as the EGDMA is a dimer of MMA, we expect the binary interaction parameter of EGDMA is same as MMA. So currently the critical parameters and eccentric factor of EGDMA is not available. So we apply the Joubert and Reid 1987 group contribution model to estimate the values. First, we identify the functional group present in EGDMA and then calculate using equations 7, 8, and 9 by applying the values from table 1. Besides that, Orbe and Sandler 1987 was an extension to Peng-Robinson equation of state, which is equation 10 and 11. By consider the polymer chain, we modify the equation with scaling concept proposed by Dejean in 1979. If the polymer chain would be in rigid rock, it's consider overestimation, and random walk model consider underestimation because there is overlapping. Normally there won't be an overlapping on polymer chain. So we consider the self-avoiding walk and modify the Orbe and Sandler equation accordingly. That's how we obtain equation 12 and 13. Table 2 shows the value that obtained from group contribution methods, and these are the parameters that we use to calculate Peng-Robinson equation of state. The figure 4 shows solubility of nitrogen in MMA and EGDMA. Open circle indicate the solubility in MMA and closed circle indicate the hypothetical value of EGDMA. When correlate the EGDMA data with Peng-Robinson equation of state and the group contribution method, we obtain two dotted line as we can see in the figure. Black dotted line is obtained from Orbe and Sandler's method, and the red dotted line is obtained from Joubert and Reid method. We expect both the line should be lower than the MMA line. In other words, higher solubility compared to the solubility in MMA. Meanwhile, Orbe and Sandler shows lower solubility and Joubert and Reid shows almost similar solubility of MMA. Both the solubility data line we obtain from group contribution method are steeper, which means lower solubility compared to the hypothetical data of EGDMA. As I mentioned previously, the binary interaction that we used are 0.224, which obtained from previous work. So we fitted the interaction parameter with the hypothetical data and we obtain a smaller value, which is negative 0.044. The value in negative indicate that there might be no key group exists in EGDMA. So in order to investigate this, we plan to conduct a real experiment in the future work. From this work, we can conclude that EGDMA was selected as a dimer of MMA to investigate the existence of key group. Hypothetical nitrogen solubility was compared with the prediction by using a cubic equation of state Peng-Robinson at 313 Kelvin. There are two group contribution methods were proposed for Peng-Robinson equation of state for EGDMA based on Joubert rate and Orbe-Sandler models. Based on comparison, hypothetical nitrogen solubility in EGDMA is far larger than the prediction by Peng-Robinson equation of state based on the two-group contribution method. So finally, we would like to convey our appreciation to Ministry of Higher Education because this work is fully funded by Ministry of Higher Education under Fundamental Research Grants Scheme. Thank you.